I'm going to be talking about the transit of Venus. And I'm gearing this talk not so much to my fellow eclipse chasers, but more to the students in the audience who far outnumber us and will be becoming the future eclipse chasers of the next generation. Well, let's start with some of the history, the rich history behind transits of Venus. Theory that the sun was the center of the solar system, or in those days, the universe. He knew of the possibility, based on his theory, that a planet might possibly pass between the Earth and the sun, particularly Venus and Mercury. But nobody knew how big the planets were back then. And he thought that Mercury and Venus were both much too small to be visible. Of course, he didn't have a telescope then either. Anyway, he recognized the possibility of transits, but nothing more than that. If we jump forward 50 years or so to Johannes Kepler, Kepler used the rich amount of observational material that Tycho Brahe had prepared as an ardent observer of the solar system, taking constant measurements of planetary positions. And Kepler was able to distill that information into his 3 laws of planetary motion, that all the planets orbit in elliptical orbits around the sun, with the sun at one focus, that if you extend a line from a planet to the sun, that line will sweep out equal areas in equal times as the planet orbits the sun. And thirdly, and more importantly for transits, that the period squared of a planet's orbit is proportional to its distance cubed. Once you've got that information, the relationship between the period of a planet and its distance, you can very quickly work out the relative positions of the planets in the solar system. This was revolutionary stuff back in the 1600s. Nobody had any idea what the distances of the planets or even the relative distances of the planets were from the sun. But Kepler was the first to demonstrate, at least qualitatively, the relative distances. If the Earth is 1 unit from the sun, he could tell, using his theory, that Venus was about 70% of the distance, and Mercury was about 39% of that distance. The one missing piece out of this is that he did not know the absolute distances. Only the relative distances could be discerned using his 3rd law. Well, near the end of Kepler's life, he published his most important publication, the Rudolphine Tables, in 1627. And that was a series of tables for predicting the positions of the planets in the future using his laws of planetary motion. And one of the things he discovered in writing this publication was that there would be a transit of Venus and a transit of Mercury just in a few years, in 1631. And he hoped to live long enough to see that. Unfortunately, he died a year earlier and didn't live for those 2 transits. Now, Pierre Gassendi, a French astronomer, did manage to observe the transit of Mercury in 1621. And when he was observing, watching for it, the accuracy of the predictions back in those days, there were large uncertainties because they didn't understand the orbits very well. And he thought that they couldn't pin down the exact time of the transit better than plus or minus 1 day. So he started observing the day before the transit, watched the day that the transit was predicted, and at one point it was a bad weather day. The sun was in and out of the clouds, and he managed to see a little tiny spot on the sun, and he thought it was a sunspot. He was expecting something much larger. But he was making drawings all along, and a few minutes later he noticed that the spot had moved, and he realized that he was seeing Mercury. He tried to observe a year later the transit of, several months later, the transit of Venus. Unfortunately, that transit, turns out, was not visible from Europe. It was visible from a different part of the world. Well, roughly at that same time, a few years later, on the scene comes a young English astronomer named Jeremiah Horrocks. And Horrocks was a very proficient student. He studied math and astronomy at Cambridge. He had a small telescope. He was making observations. He observed the occultation of the moon occulting the Pleiades. and I believe he was the first to actually demonstrate that the moon's orbit was elliptical. He was only 16 or 17 years old, so think about that. He also started calculating the positions of the planets into the future, and he had slightly better, or he thought a slight error in one of Kepler's numbers for the orbit of Venus, and he made a correction to it. And when he did that, he discovered that there was probably going to be a possible transit of Venus in 1639 that Kepler had missed. So he contacted his brother, and he contacted a friend, William Crabtree, to begin watching the sun the day before the predicted time of the transit, because again, there was a large uncertainty, a day or two, in when the transit was going to take place. And he started observing from the place where he was living, a place called Carr House in a little town called Hoole in northern England. And he began observing the day before the transit. And his primary goal in observing this transit of Venus was to try to measure the diameter of Venus with respect to the diameter of the sun, because nobody knew how big the planets were. He used a small Galilean telescope to project an image of the sun into a darkened room, produced a 6-inch diameter image of the sun, and he had started observing the day before the transit, didn't see anything. The day of the transit, he observed for most of the morning. The sun was in and out of the clouds a bit. He had to go take care of some official duties regarding Hoole Church, where he worked as a cleric. And he got back to his apartment back in the afternoon at 3:15. He turned his telescope back on the sun, and lo and behold, the transit of Venus was already in progress. And sunset only took place a few minutes later at 3:50. So he only had about a 40-minute or so window to make his observations. And this is a drawing showing Venus moving across the disk of the sun, and he was able to make a measurement, the first accurate measurement of the Venus transit, where he measured the diameter of Venus as 1 minute 12 seconds. The actual value that we know now is about 1 minute and 1 second, so he was pretty close. Well, his friend William Crabtree also observed the transit, and he got similar results. He actually made a slightly better measurement. Unfortunately, Jeremiah Horrocks died the day before he was going to meet with Crabtree to discuss the results of their observations. And Crabtree died a few years later. So these two promising astronomers died early in their careers. This is a view of the church where Horrocks worked. My wife and I had a chance to visit Hoole back in the fall of 2003, 6 months before the 2004 transit. And the church has this beautiful stained glass window with a commemorative stained glass etching of Horrocks observing the transit. And we visited the home of Horrocks, Carr House, and actually got a chance to look out the same window, purportedly where Horrocks had his telescope set up to project this image of Venus into the room. Well, since that first transit in 1621, if we don't count this 2004 transit, there have only been 6 transits in 3 centuries. Why are transits of Venus so rare? To understand that, we have to look at the geometry of the Earth and Venus as they orbit the sun. And here we've got the Earth in the outer orbit, Venus in the inner orbit, at inferior conjunction. Venus lies between the Earth and the sun. And this is the geometry you need for a transit. Now let's assume this is a racetrack, and we start the clock and we watch Venus and Earth start to orbit. Now Venus is closer to the sun than the Earth, so it travels around in its orbit much faster. If we allow 1 year to elapse, Earth has made 1 complete revolution and it's back to its starting point. Venus, on the other hand, has made 1 2/3 laps around and is still catching up to the Earth. They haven't lined up again in inferior conjunction yet. If we wait a period of 583 days, we find that Venus and Earth finally catch up with each other again and form inferior conjunction. But notice they're in a very different part of their orbit than when they started out. They were originally down here. So that's in 583 days. That's called the synodic period of Venus. It's the amount of time it takes for Venus to line up in the same position with respect to the Sun as seen from the Earth. Well, it turns out that if you allow several more synodic periods to elapse, you find that in the course of 8 years, 8 Earth years, Venus and Earth will line up again in inferior conjunction in almost the exact same spot they started. So 5 synodic periods of Venus is equal to just under 8 Earth years. And this is an important period when it comes to calculating transits and understanding the mechanics of transits. This corresponds to 13 orbits of Venus around the Sun compared to 8 orbits of the Earth around the Sun. So astronomers say that Venus and Earth are locked in a 13 to 8 orbital resonance. Now that resonance isn't perfect. There's a slight lag of about 2.5 days, so it slowly shifts over the centuries. If we look at the Earth and Venus from an angle, their orbits, we see that Venus's orbit is tipped about 3.4 degrees to the Earth's orbit around the Sun. And that means that as they intersect, there's this line of nodes between the two planes, the plane of the Earth's orbit, the plane of Venus's orbit. And Venus passes through the ascending node, passing from south to north. During December, if Earth is at the line of nodes, and Venus passes through the descending node in June for a transit to take place. So the conditions required for a transit of Venus is Venus has to be in inferior conjunction. It has to be between the Earth and the Sun. And it also has to be at one of the orbital nodes. So in order for these two conditions to take place, it can only take place during the seasons of early December and early June, at least right now, during this period in history. Going back to this diagram of the historical transits, we can now add 2004 and 2012 onto the diagram, and you'll notice some patterns starting to emerge when you look at these different transits. The first 2 transits, you've got a gap of 8 years, followed by 121.5 years before you get another pair of transits separated by 8 years. After that, there's a gap of 105.5 years. You get another pair of 8-year transits, or double, sometimes called a double transit, followed again by 121.5 years. Well, transits of Venus can be grouped into families, just like solar and lunar eclipses, Saros-like families of repetition. And I've drawn a box here around 4 different Venus transit cycles that are currently going on. And you'll notice that each member in a transit family is separated by 243 years. So the 1621 and the 1874 transits are part of one Saros series, where every single member is separated by 243 years. And the same thing goes for these other 3 series. And they're all going on concurrently at the same time. Well, on the NASA Eclipse website, I've got a catalog, a 6,000-year catalog of Venus transits. And we can look a little bit at some of the statistics of all transits taking place during that period. There are